Welcome students to lecture number 11 for the MOOCs course on fuzzy sets, arithmetic and logic. In the last class, we have seen multiplication of fuzzy numbers. In particular, we have seen the example of multiplying A is equal to the triangular fuzzy number minus 1, 1, 3 with B, which is equal to 1, 3 and 5. And the solution came through interval arithmetic. So, we had alpha cut of A is equal to 2 alpha minus 1 to 3 minus 2 alpha, and alpha cut of B, it was 2 alpha plus 1 to 5 minus 2 alpha, and we obtained the alpha cut of A multiplied with B is equal to minus 4 alpha square plus 12 alpha minus 5 to 4 alpha square minus 16 alpha plus 15, this interval when alpha less than equal to half, and we have got the interval 4 alpha square minus 1 to 4 alpha square minus 16 alpha plus 15, this interval when alpha is greater than half. In a similar way, we can compute A divided by B. Since A is a fuzzy number and B is a fuzzy number, A divided by B is also going to be a fuzzy number. And how do you get the alpha cut of this? So, alpha cut of A divided by B is equal to minimum of 2 alpha minus 1 upon 2 alpha plus 1, 3 minus 2 alpha upon 2 alpha plus 1, 2 alpha minus 1 upon 5 minus 2 alpha, and 3 minus 2 alpha upon 5 minus 2 alpha. So, we have to compute these 4 quantities, and then depending upon the value of alpha, we have to see in which range which of the expressions is minimum, and the upper bound is going to be maximum of the same 4 quantities, and thus we get a closed interval which is running for different values for alpha, the minimum of this to the maximum of the same 4 elements. The way we have drawn the curve for multiplication, in a similar way you can draw the curves for the 4 functions for alpha is equal to 0 to 1, and from there you can calculate exactly the alpha cut for different values of alpha. I leave that as an exercise, but I am giving you the answer. The membership function of mu a by b of x is going to be something like this. It is 0 if x is less than minus 1 and x is greater than equal to 3. It is x plus 1 upon 2 minus 2x for minus 1 less than equal to x less than 0. This is equal to 5x plus 1 upon 2x plus 2 for 0 less than equal to x less than 1 by 3, and this is going to be 5 minus x upon 2x plus 2 for 1 by 3 less than equal to x less than equal to 3. Thus, the membership function changes at different intervals, and we can see that since we had these to be a and this to be b, the minimum value that is coming out to be minus 1 by 1, and the maximum value will come when I am dividing 3 by 1, that is 3. Therefore, the support of mu a plus b is going to be from minus 1 to 3. I leave this as an exercise for you to complete this and see whether you can actually arrive at this answer when you are using the analytical aspect of the 4 curves that I have just mentioned, and see how they are behaving for different values of alpha between 0 to 1. Now, let me proceed with triangular approximation of fuzzy numbers. We have seen that if A and B are triangular fuzzy numbers, then A plus B is a triangular fuzzy number, and similarly A minus B is a triangular fuzzy number. The advantage of triangular fuzzy number I have already explained, that because of the linearity of the left hand side of the membership function and the right hand side of the membership function, it is very easy to calculate the alpha cuts and also to compute the membership functions very easily from the linear aspect of the Lx and Rx. Hence, we have a constant tendency to convert a fuzzy number into a TFN, because that makes our life very easy. But we have seen that for multiplication and division, the resulting fuzzy number is not a triangular fuzzy number, although the fuzzy numbers we operated on have been triangular fuzzy number. Hence comes the question of linear approximation of a fuzzy number. So, let us first start with multiplication. Example 1, TFN approximation of A star B when A and B are triangular fuzzy numbers. How to do that? So, consider A1, B1, C1 star A2, B2, C2. We can get the following: alpha cut of A is equal to A1 C1 when alpha is equal to 0 and alpha cut of B is equal to A2 C2 when alpha is equal to 0. Therefore, by interval arithmetic, alpha cut of A dot B will be minimum of A1 A2, C1 A2, A1 C2 and C1 C2, that is the lower bound, and upper bound is going to be maximum of these 4 quantities. So, from this we get the support of A star B and alpha cut of A is equal to B1 for alpha is equal to 1 and alpha cut of B is equal to B2 for alpha is equal to 1. Therefore, one cut of A star B is by interval arithmetic is simply B1 B2. Thus, from the 0 cut of A star B, we get the support of the fuzzy number A star B, and from the one cut of A star B, we get the modal point of A star B. So, if we plot it, we got the 3 important points for A star B. But the problem is the Lx and Rx, instead of being linear, they have a quadratic form or combination of two different quadratic functions, as we have seen in our last class that we have got something like this as the membership function for A star B. Our aim is to approximate it using a linear function or using linear functions. That is, we are trying to have lines like this so that the fuzzy number A star B is approximate by the TFN, let us call it P. How to do that? We shall look at this region. This is the discrepancy between the approximated straight line and the actual curve. This is on the left hand side and this is on the right hand side. So, the green region gives the discrepancy. Our aim is to see the extent of the discrepancy which we often call divergence in comparison with the actual fuzzy membership. Question is how to do that? In order to explain that, we first look at some single variable functions such as A inverse e to the power a, log a. All these are nonlinear functions and therefore, they need linear approximations for easy handling. On the other hand, A star B, A divided by B, etcetera, are functions of two variables. So, in the next class, we shall check A star B in more details. So, example, let us consider A inverse, where A is an arbitrary fuzzy number, that is TFN, triangular fuzzy number A, B, C. Note that A comma B comma C are all greater than 0. This is because if we want to take A inverse, that is 1 upon A, then 0 cannot be a part of A, this A. We know that the alpha cut of A is equal to A plus B minus A alpha comma C minus B alpha. Therefore, by interval operation, alpha cut of A inverse is equal to 1 upon C minus B alpha to 1 upon A plus B minus A alpha. On the other hand, since we want to approximate it with a TFN, the most natural approximation is P is equal to 1 upon C, 1 upon B, 1 upon A. This should be very clear, as C is greater than B and greater than A. When we take reciprocal, 1 upon C, 1 upon B, 1 upon A is the corresponding TFN. Therefore, alpha cut of P is equal to one upon C minus 1 upon C minus 1 upon B alpha to 1 upon A minus 1 upon A minus 1 upon B alpha. We need to check the amount of discrepancy on both left hand side and right hand side. Therefore, we do the following. On the left hand side, the difference between alpha cut of A inverse and alpha cut of P is equal to 1 upon C minus B alpha minus 1 upon C plus 1 upon C minus 1 upon B alpha, and on the right hand side the discrepancy is 1 upon A plus B minus A alpha minus 1 upon A plus 1 upon A minus 1 upon B alpha. We need to check the acceptability of P in place of A inverse. The difference on the left hand side is, if we call it epsilon L alpha, this is equal to 1 upon C minus B alpha minus 1 upon C minus 1 upon B minus 1 upon C alpha. So, this is a function of epsilon. We need to find out where it is maximum. So, we differentiate it with respect to alpha. So, I am differentiating this. This is equal to 1 upon C minus B alpha whole square, because it is alpha is equal to minus 1 multiplied by minus 1 multiplied by minus C minus B minus differentiating this with respect to alpha 1 upon b minus 1 upon c. Which is equal to c minus b upon c minus b alpha whole square minus 1 upon b minus 1 upon c. So, to get the maximum, we equate it to 0. Therefore, what we get is c minus b upon c minus b alpha whole square is equal to 1 upon b minus 1 upon c is equal to c minus b upon bc. So, we can cancel out the numerator, and therefore, what we are getting is c minus b alpha whole square is equal to bc. Therefore, c minus b alpha is equal to root over bc. Therefore, alpha star L, that is the alpha where maximum divergence occurs, is c minus root over bc upon c minus b. Question is, what is the value of that divergence? In order to obtain that, we replace alpha in the expression epsilon L alpha with alpha star L, and we get the following. Therefore, maximum divergence is 1 upon c minus b multiplied by c minus root bc upon c minus b minus 1 upon c minus c minus b upon bc star c minus root bc upon c minus b, which is equal to, if you simplify, 1 upon c minus root bc minus 1 upon c minus c minus root bc upon bc is equal to 1 upon root bc, as this c and this c cancels out, minus 1 upon c minus c minus root bc upon bc is equal to, if we take bc common, it is root bc minus b minus c plus root over bc is equal to minus of b plus c minus twice root bc upon bc is equal to minus of root b minus root c upon root bc whole square is equal to minus of 1 upon root b minus 1 upon root c whole square. So, this is a general formula. For a particular problem, we can substitute the value for a, b, c and we can get the maximum divergence. In a similar way, one can find that epsilon r alpha, that is a right side discrepancy, at alpha, and one can find the maximum value of right side divergence is equal to epsilon star or alpha is equal to minus 1 upon root a minus 1 upon root b whole square. So, these two values are very important for us to solve the problem. So, let me give you an example. Consider a is equal to 4, 9, 16. This is a triangular fuzzy number. Therefore, A inverse can be approximated by the fuzzy TFN P, which is equal to 1 by 16, 1 by 9, 1 by 4, and we have the maximum divergence on left hand side is minus 1 upon root b minus 1 upon root c whole square is equal to minus 1 upon root b is 1 upon 3 minus 1 upon 4 whole square is equal to minus 1 upon 12 whole square. Similarly, the maximum divergence on right hand side epsilon star or alpha is equal to minus 1 upon root a, which is 2, minus 1 upon root b, which is 3 whole square is equal to minus 1 upon 6 whole square. Therefore, if we take their absolute values, we can see that the maximum divergence on left hand side is modulus of 1 upon 12 square is equal to 1 upon 144, and on right hand side is equal to 1 upon 36. Question is whether it is acceptable or not. As we can see, these are pretty small numbers in comparison with the overall spread of the fuzzy number, which is from 4 to 16. That was the support for original number with the peak value at 9. In comparison, these are very small. So, for all practical purpose, we can accept this. That is 1 upon 16, 1 upon 9, 1 upon 4, these TFN as inverse of 4, 9, 16. Okay, students, let me consider another problem for approximation of exponentiation of fuzzy numbers. E to the power a, where a is a TFN, that is a triangular fuzzy number, and our aim is to approximate it with another fuzzy number. So, let us consider A is equal to A, B, C belonging to R plus. That is, all A, B and C are positive real numbers. Therefore, alpha cut of A is equal to, as we all know, it is A plus B minus A alpha to C minus B alpha. Therefore, alpha cut of A or e to the power A may be considered as e to the power A plus B minus A alpha, comma, e to the power C minus B alpha. So, as before, we are applying the arithmetic operations on corresponding alpha cuts to get alpha cut of the result, which is e to the power a. Let P be the linear approximation for e to the power a. Then, by a similar approach, P can be the triangular fuzzy number e to the power a, e to the power b, e to the power c. Since all a, b and c are positive, therefore, exponentiation is an increasing function. So, we need not worry about their relative ordering, and we are going to get this. Therefore, alpha cut of p is equal to e to the power a plus e to the power b minus e to the power a alpha to e to the power c minus e to the power c minus e to the power b alpha. Therefore, left hand side divergence alpha is equal to e to the power a plus b minus a alpha minus e to the power a minus e to the power b minus e to the power a alpha, because from interval arithmetic this is what we have got. By the triangular approximation we have got this. Therefore, their difference is giving us the divergence, which is epsilon L alpha, and in a similar way epsilon r alpha is equal to e to the power c minus b alpha minus e to the power c plus e to the power c minus e to the power b alpha. We need to check where the maximum occurs and what is the value. So, epsilon L alpha is equal to e to the power a plus b minus a alpha minus e to the power a minus e to the power b minus e to the power a alpha. Therefore, epsilon prime L alpha, which we get by differentiating this with respect to alpha, is equal to e to the power a plus b minus a alpha multiplied by b minus a minus e to the power b minus e to the power a. By equating to 0, we have e to the power a plus b minus a alpha is equal to e to the power b minus e to the power a upon b minus a, or a plus b minus a alpha is equal to log of e to the power b minus e to the power a upon b minus a, or alpha star is equal to, let me call it alpha star L, is equal to minus a upon b minus a plus 1 upon b minus a into log of e to the power b minus e to the power a upon b minus a. So, this is the value of alpha where the maximum divergence will occur on the left hand side. In a similar way, one can find that epsilon star r is equal to c upon c minus b minus 1 upon c minus b into log of e to the power c minus e to the power b upon c minus b. Therefore, for a given problem, we need to compute the maximum value of the divergence by putting in these values in the respective expression. So, let me give you an example. Consider A is equal to 0.5, 1 and 2. Therefore, alpha cut of A is equal to 0.5 plus 0.5 alpha comma 2 minus alpha. Therefore, alpha cut of e to the power a is equal to e to the power 0.5 plus 0.5 alpha to e to the power 2 minus alpha. On the other hand, the TFN approximation is equal to P, which is equal to the triangular fuzzy number e to the power 0.5 e and e square. Therefore, alpha cut of P is equal to e to the power 0.5 plus e minus e to the power 0.5 alpha to e square minus e square minus e into alpha. Therefore, alpha star L, which is equal to minus a upon b minus a plus 1 upon b minus a into log of e to the power b minus e to the power a upon b minus a is equal to minus 0.5 upon 1 minus 0.5 plus 1 upon 1 minus 0.5 log of e to the power 1 minus e to the power 0.5 upon 0.5, which will come out to be approximately 0.52, and therefore, maximum divergence on LHS is, by putting this value, is e to the power 0.5 plus 0.5 into 0.52 minus e to the power 0.5 minus e minus e to the power 0.5 into 0.52, and this is coming out to be 0.67. So, this is the maximum divergence on the left hand side. In a similar way, we can compute maximum divergence on the right hand side will come out to be roughly equal to minus 0.56. Therefore, if we compare this divergence in comparison with the real number e square and e to the power 0.5, we find that these values are quite small in comparison with the overall triangular fuzzy number. Hence, for a practical application, we may use, since these values are small, we can approximate the fuzzy number e to the power a by the TFN e to the power a, e to the power b, e to the power c. Okay, friends, I stop here today. In the next class, I shall show how we can use triangular approximation for a function between two numbers. In particular, I shall work on fuzzy multiplication, and then I will discuss how to order a set of fuzzy numbers linearly, or in other words, how to sort a set of fuzzy numbers. Okay, friends, thank you so much.